All right, let's learn about the difference between static and kinetic friction. And we'll start learning about static and kinetic friction by just imagining a simple scenario that you guys already played with last week of a person just pushing an object. So I'm going to open up the simulation you guys have already played around with a little bit to demonstrate a couple quick things. I have the man here, I have the boxes he's going to push, and you can see that I have some friction in this one. So if he pushes on the object, you can see that his applied force and the frictional force are exactly the same. And this should match your experience. If you push gently on an object, it doesn't immediately start moving because it has some friction keeping it in place. And if I increase this slowly, you can see that as I increase frictional force, applied force is increasing at the exact same rate. And the vectors are getting longer, but notice that nothing's moving yet because every time applied force increases, frictional force also increases. So I've increased it up to the first 50. Let's go to our graph here. We've seen that so far, at least, they've increased at a 1-to-1 ratio. So if I go back, I'm going to start increasing by a little bit bigger ratios. Oops, that's not how I do that. There we go. Increase by bigger ratios, and let's go up another 50. Oops, 150. Okay, it just increased again, another 50, another 50, and another 50. So I've increased it quite a few times, and every time that I increased it, normal force and applied force and frictional force increased at the exact same rate. So my graph is going to look like this. It's totally linear, constant slope, all those kind of things. But I'm actually at a moment right here, and I just know this because I played around with it before I started the video, a moment called the threshold of motion. And the threshold of motion is that moment right before an object moves. So you can imagine that an object would stay still, stay still, stay still, and then at some moment it will be moving. And right between those two is the threshold of motion, right when it's just about to move. It's still not moving, or it's literally the very first instant that it starts moving. So like right there is my threshold of motion. And so looking at my threshold of motion, watch what happens when I go to the very next, add 1 more newton. So I'm going to do that, and bam. If you look at it right there, all of a sudden my frictional force just dropped to 188. And now that it's moving, I can keep increasing it, and notice that frictional force is staying right at 188. I can really, really push on this thing, and no matter how high I get it, it stayed at 188. So let's go back to our graph and talk about what just happened. As we crossed the threshold of motion, it suddenly dropped down and started maintaining a constant value. And what happened is we just crossed from something called static friction to kinetic friction. And they have some different behaviors that you need to be aware of. Static friction is going to just be defined in our class as the surfaces have no relative motion. That means that the surfaces are not moving past each other. They are always relative to each other in contact. That's true of any object that's not moving, and the most common one that students overlook is something like tires or somebody walking. Tires that are rolling across the ground, they're not moving relative to the surface. They stay in contact as they go around. Sure, the car is moving and the tires are rotating, but the surfaces are staying relatively stationary to each other. The same thing is true of your foot. While you move as you walk, as your foot comes down and pushes you forward, it's staying, it has no relative motion. So that's static friction, when the surfaces aren't actually moving past each other. And the important thing to know about static friction is while we have this formula, force of friction is equal to mu normal force, this little s right here represents this is the static coefficient. There's always a slightly different coefficient for static versus kinetic. And you can see that right here. This is the difference between mu s, the maximum value, and mu k, the minimum value, or the kinetic value. So this formula right here doesn't work very well for normal force. It actually gives the up to the max But you guys just saw that force of friction was not always at its maximum value when we did static. It was always just enough to keep it in equilibrium up until the object started moving. So only at this moment here, at the threshold of motion, did we have the max force of friction. So this formula doesn't work very well in static scenarios because it only gives us the max value. It's always less than or equal to, and that's where that came from in the last video, the less than or equal to. So I don't suggest using this formula when you know that it's static friction, because you'll always overestimate it unless you know it's at the threshold of motion. The better way to do it is use equilibrium. So a quick example with that, I have this object right here. It has a mass of 60 kilograms. The coefficient of friction is 0.65. Let's just make the assumption, or let's draw the free body diagram real fast. It has a force of gravity, which would end up being equal to 600 newtons. Since it's in vertical equilibrium, the normal force would be equal to 600 newtons. And if I use this formula and said force of friction is equal to 0.65, that's the coefficient of friction, times 600 newtons, that's the normal force, I would end up saying the force of friction is equal to, I wrote it down somewhere, 390 newtons. Okay, that's a big value, but it's not even moving. Nobody's pushing on this. If this thing had a force of friction of 390 newtons somewhere along this axis, which direction is it going? And it's not moving. It can't have a horizontal force of friction in either direction. Otherwise, friction somehow moves it. So if I then said instead, somebody's pushing it 50 newtons that way, the mistake that comes up is a student assumes, oh, that must mean that it has 390 in the opposite direction. But if that was true, now the object's actually going to start accelerating back that direction, even though it's supposed to be stable. So the actual force of friction would only be 50 newtons, because that's all it takes to keep the object in place. If I pushed harder with 100, force of friction increases to 100. If I push harder, it gets up to eventually 390. And then if I push just a smidge more, we stop having static friction and go into kinetic friction, where now we have objects that are sliding past each other. So this is surfaces that slide past each other. If we're doing kinetic friction, then this is the formula to go with. And you ask no questions. You can just move on with your life. It's very quick, easy. You just find normal force, multiply it by the coefficient. There you go. You have kinetic friction. So you can use this always for kinetic friction. You can only use it sometimes for static. You can use it if you know it's at the threshold of motion for static friction. Otherwise, you need to be using equilibrium. So that's kinetic friction. It's honestly the much easier one. So if I was doing a similar scenario here, let's say that the coefficient of kinetic friction was 0.45, while the coefficient of static friction was 0.65. So if I already knew it was moving, then I could figure this out using much the same math that we used earlier. I know it has a mass of 60, so it has a force of gravity of 600. That means the normal force is also 600. So if I want to calculate the force of friction, it would just be 0.45 times 600 newtons. And that would give me a value of 270 newtons, which is totally accurate, and there's no problem with that. Last thing to mention is just up in this top corner. What's often done is an experiment where you're trying to find the coefficient of friction. And since if you used this as your y value and you used this as your x value, so there's my y, there's my x, then this must be my slope. So a lot of the times experiments are done either where you're trying to find the coefficient of kinetic friction by dragging something at a constant speed, or you're trying to find the coefficient of static friction by pulling it up till you get to that moment of the maximum static friction, and then you record those. So that hits pretty much everything we need to know on static versus kinetic friction. One more time, just be very, very careful when you're doing your static friction that you don't overestimate the value. So thanks for watching. See you around.